Is the
Is
screen
the screen?
visible?
Yes, the screen is visible.
Yeah. Good. Okay. In that case, I'll start. And
And
so most of this talk will just be an extension of the previous talk. We will go further into maximal ideals, and then we'll introduce some special integral domains and their properties. So again, just like last talk, I just want to give a quick recap, but it shouldn't take too long since I'll just give three or four of the essential results that we'll be using, and then we can move on with the rest of the theory. So, well, the first thing, of course, would be the definition of an ideal. Uh, so, we'll recap the definition of an ideal. So, given a commutative ring with unity R, so when ring R again, when I say a ring over here, I mean a commutative ring with unity. Given a ring R, subset I of R is said to be an ideal if it satisfies the two following properties. The first one being A plus B always belongs to the ideal if A and B belong to the ideal, which is that the ideal is closed under addition. And the second one is that for any A belonging to the ideal and any element R of the ring, we have AR belongs to the ideal. So we had these two. So we had multiple kinds of ideals, and we also defined what it means for something for a subset of R to generate an ideal. So one more thing is if we have a subset A equal to let's say A1 AN to be a subset of the ring R, then the ideal generated by A1 to AN, which is given by the same notion of the basis of a vector space, I mean, same notation, is said to be all R linear combinations. So these are called R linear combinations of these elements, R linear combinations. And they are precisely the following, which is the taking any coefficient r and multiplying it by the ai. So the sum ri ai as I ranges from 1 to n and ri lies in r for all I. So this is what it means for an ideal to be generated by a certain subset of R. And of course, the most trivial examples of such ideals are ideals generated by a single element, ideals generated a single element. And these are, of course, of the form bracket A, which is basically all elements, as you could guess, of the form Ra, where R belongs to R. So it's basically all R multiples of the single element A. So these are called principal ideals. Yeah. So there is a bit more that I would like to recap. So yeah, then we come to a certain special family of ideals known as maximal ideals. And here, these are ideals that are properly contained in R, yet no, they are not contained in any ideal of R apart from themselves and R. So I is a, wait, let's not take a subset. Let's assume that it's an ideal. Uh, so an ideal I of R is like to be a maximal ideal if I is properly contained in R. So can emphasize that by saying the subset but not equal to of R. And second, the only ideals that contain I are R and I itself. All right. So I think apart from these, I will just need to state two or three results that we have done before. So I'll begin by stating them now. So the first one, okay, let's say these are a few results. The first one being that a field, oh wait, all right, wait. A ring F is a field, and you may recall that a field is nothing but a ring in which every nice property that we want is satisfied, which is the additional fact that multiplication is also closed under inverses for all non-zero elements. So a ring F is a field if and only if F has exactly two ideals, which are the zero ideal, which is the ideal generated by zero, and and all of F, which is basically the ideal generated by one. Since all of F is every element of F multiplied by one, so it's all F multiples of one. So that is the ideal generated by one. So these two have to be the only ideals. And as you can see here, it's pretty obvious that since there are only two ideals, a field has a maximal ideal. I mean, every ring has a maximal ideal, as you have seen from Zorn's lemma in the previous talk. So the maximal ideal of this field is zero. So the maximal ideal of any field is the zero ideal, which is zero. I say the maximal ideal here, and it might hint to the notion that every field contains only one maximal ideal, which is wrong. I mean, which might hint to the notion that every ring contains one maximal ideal, which is wrong. But in the case of a field, the maximal ideal is unique since there are only two ideals and only one of them is a proper ideal, that is zero. So this is not generally true in the case of any arbitrary ring. A ring can contain multiple maximal ideals and as we have seen before itself, the ring Z. In Z, maximal ideals, uh, uh, in Z, maximal ideals are of the form, what were they? They were all the prime prime rings. So they were all of the form PZ, which is equal to all multiples of P, 2P minus P, minus 2P, so on. Yeah. So of course, as you can see here, oh, and that P has to be a prime. So as you can see here, Z, the ring Z contains multiple maximal ideals, and it contains, in fact, countably many maximal ideals, which are generated by the primes in Z. All right. So now that we have covered this, uh, sorry about that. Now that we have covered this, this was the first result. The second result is the fact that Uh, yeah. So if yeah, uh, in a ring I, sorry, in a ring R, in a ring R, I is a maximal ideal of R if and only if R by I is a field. And this we have made continuous use of this the result that I've just stated in the previous talk multiple number of times. So we will be using this fundamental result again. for the rest of today's talk. So, and the last one being that we calculated the maximal ideals for several known rings such as Z, uh, uh, the fields, etc. And the last one was a very fundamental result about polynomial rings. So, polynomials over fields. So, if F is a field, we consider the polynomial ring Ft, and the maximal ideals of Ft, which are represented by max Ft, as we discussed in the last talk, are precisely the set of all monic irreducible polynomials in Ft. Not the set of all monic irreducibles, but the set of all ideals generated by monic irreducible. So more precisely, it is the set of all ideals generated by a single polynomial, Ft, such that Ft is a polynomial in this ring of polynomials over F, and F is monic irreducible in F. So to recap, uh, Ft is irreducible. Basically means that degree of Ft is greater than equal to 1, and there do not exist polynomials Ht and Gt that belong to Ft, so that Ft equals to Ht into Gt. Of course, the degree of both Ht and degree of Gt should be greater than or equal to 1. Otherwise, there is always a trivial decomposition by factoring out a scalar from the field. So here we basically say that Ft is irreducible if it is of degree greater than or equal to 1, and it cannot be broken down into two. It cannot be expressed as the product of two polynomials with degree greater than or equal to 1. And that is pretty much more or less intuitive from the very word irreducible. So, yeah, the maximal ideals of a polynomial ring over a field F are precisely the principal ideals generated by monic irreducibles in the field F. So now we can try to extend this notion, and the next result that I'll be giving, it's a very fundamental theory. It's a very fundamental result which actually is a special case of Hilbert's Nullstellan set, if you may have heard of it. So to start with that, uh, we consider the irreducibles first in R of X. So in R of X, the ring merits only two kinds of irreducibles. First of all the linear, all the linear polynomials in R of X are trivially irreducibles, since every linear polynomial in any polynomial ring is always irreducible, because you can never decompose a linear polynomial into a product of more than uh, into a product of two polynomials with degree greater than or equal to one. So yeah, we have, so the first category will be x minus alpha, these kind of polynomials such that alpha belongs to R. But we also have a second category of irreducibles, and those are precisely the quadratics in R. And although not all quadratics in R are irreducible, we have quadratics of the form x minus alpha and to x minus alpha conjugate, where alpha is a complex number. So these are the only two irreducibles in R. Although the proof may look trivial, it is actually a consequence of the fundamental theorem of algebra, which we will not be proving here, although it deserves a separate talk on its own. So, since we know that in over the field of complex numbers, every polynomial can be split into linear factors. It is a trivial byproduct that the only two types of irreducibles over Rx are the linears and special quadratics, whose both roots are complex. So any polynomial of degree greater than or equal to 3 in R of x can be split into two smaller polynomials of degree greater than equal to 1 in R of x. And the second case that we consider is precisely the irreducibles in the complex numbers. And as we know from the fundamental theorem of algebra, that every polynomial in the complex field can be split into unique linear factors. So that will imply that the only irreducible polynomials over C are of the form x minus alpha, i.e., the linear polynomial, where alpha belongs to C, some complex number. Oh, by the way, also here I should mention that alpha belongs to C and does not belong to R. Because if alpha belongs to R, then this very product is a trivial splitting of the polynomial. But if alpha belongs to C, then we can get no further splitting of the polynomial. So yeah, we have that. So now the first proposition that we come across is that we attempt to find the maximal ideals over the field C of x1, x2, xn. That is uh, n-variate polynomials over the field of complex numbers. So yeah, so here we basically consider the polynomial ring C over n variables x1 to xn, and we attempt to ask what the maximal ideals should be. So first off, if we use our intuition here, we know that the linear factors are the only irreducible polynomials over Cx. So one might expect that the ideals generated by each linear factor over every variable should be a maximal ideal. And that in fact turns out to be true. So since we have that the ideal x1 minus a1, the ideal generated by x1 minus a1 till xn minus an is basically given by the following. Since we defined what it means to for an ideal to be generated by a certain set, it is the set of this ideal basically contains the set of all polynomials g, which is given by I equal to 1 to n, any element of c x1 to xn, which we will say gi x1 to xn. Uh, so that is basically gi x1 xn into an element of the generator set xi minus ai, such that gi is a polynomial in the x1 xn. So this is basically the ideal that we are talking about here, right? This is a more precise definition since it gives the form of every element of the ideal. So let So our in this proposition, we basically prove that this ideal that we are talking about here is in fact a maximal ideal. So let us say since we defined A in the proposition to be equal to A1 to AN, let us say MA is given by this ideal x1 minus A1 till xn minus AN. So now we have an evaluation map as shown in the first talk, theta A from C x1 to xn to C. So this evaluation map basically evaluates every polynomial in C x1 to xn by substituting it with the vector A. So basically what that does is theta A of some polynomial f x1 xn basically goes to oh wait, my bad. Yeah, basically goes to f a1 to an. And now we use this evaluation map and we use some properties of this evaluation map. So we notice that theta A is a surjective ring homomorphism, and I mean, it's pretty obvious that it's a ring homomorphism, as it was discussed. The question is, why is it surjective? So the thing is, we know that C is in fact a subset of C x1 xn, and our map, our theta, the range of our map theta A is C, and we know, and it is fairly obvious that theta A of any complex number Z, or I'd rather say of any complex number C, which belongs to C, is equal to C itself. Since C basically on the left side represents all the constant polynomial C, and C on the right side is the evaluation of the constant polynomial, which is the constant that represents itself. So this basically implies that theta A of the subset C is equal to C. So every element of the complex number has a unique preimage in the ring of n-variate polynomials. And now we also have C is a field, and theta A basically, I'll emphasize this again, theta A maps from C x1 xn to C. And this C is a field. And we basically have a homomorphism from a ring to a field. So therefore, the kernel of theta A will be maximal. This follows from the first isomorphism theorem, which basically stated, and since we do have this map, this first isomorphism theorem basically implies that since kernel theta A is basically, I mean, yeah, we have the kernel of theta A, we have that C x1 to xn over the kernel of theta A is isomorphic to C itself, which follows from the first isomorphism theorem. But we know from the fundamental result that since this is a field and it's isomorphic to this, so this also must be a field. So, and this is an ideal of this, which from one of the fundamental results that we described implies that curve theta A is a maximal ideal. All right. So all we are left to show is that curve theta A. So we are left to show that the kernel of theta A, which we prove to be a maximal ideal, is indeed this very ideal that we started out with, to x minus a n. So it so now it is obvious. The following are obvious. It's obvious that xi minus ai belongs to the kernel of theta A for all I belonging to 1 to n, since theta A of xi minus ai basically evaluates xi minus ai at the vector A, and that gives ai minus ai, which is equal to 0. So it belongs to the kernel. So since each of the polynomials of this form belongs to the kernel of theta A, we can basically then conclude that the ideal generated by xi minus ai, I mean, the ideal generated by each of these, which is the ideal generated by x1 minus a1, x2 minus a2, comma, xn minus an, will be contained in the kernel of theta. So we have proved a one-way inclusion. Now we just have to prove, so we need to show that the inclusion other way holds. So we need to show the following, that is, the kernel of theta A is contained in x1 minus a1 till xn minus an. Right. So now we start. doing this by considering an arbitrary element of the kernel of theta. So let f x1 to xn lie in the kernel of theta a. So and uh, let us further specify what f x1 to xn looks like. So let us say f x1 to xn is of the form uh, where we run over all finite sums of b b I1 to IM of x1 power I1 till xn power IN. So this should make a fair amount of sense since this is a general representation for n-variate polynomials in over a certain field. So of course here B I1 to IM belongs to C. Right. So we have this representation. So now, what we do is, in fact, let me copy this representation so that I can use it for the manipulation that we'll do next. So let's just copy this. My bad. Yeah. So we use this representation of f x1 to xn, which we assumed was an arbitrary element in the kernel of theta. So now what we do is we actually represent it in a better way. We say let f x1 to xn, let us instead represent it as this summation. So again, it goes over all finite such sums and takes the coefficient b I1 to IN. And here, each of these terms, xi power or xk power ik, we represent it as, so starting with x1, we say x1 power I1 is basically x1 minus a1 plus a1 power I1. Similarly, we do this all the way till xn, which gives us xn minus an plus an power in. So this is how we choose to represent it. Now, once we use the binomial theorem and expand out all the terms, uh, we get a certain form in which once we take out all these constant powers at the end, which is ai power a1 power I1 till an power in, we take them out separately, and that gives us it is equal to this finite sum, which is b I1 till in of a1 power I1 an power in. It is equal to taking the constants out plus another polynomial in terms, since every other term will have some factor of xi or xk. So it will be the remainder will be some polynomial x1 to xn without any constant term, i.e., every term here has some x variable in it. So here here we have that since we took out the constant term, this g x1 to xn must contain all multiples of x1 minus a1, powers of xi minus ai. So it is basically such that every term here is a multiple of some xi minus ai power, or to be more precise, xk minus xk power ik. So therefore, since it every term here is a multiple of that, we can conclude that g x1 to xn actually belongs to the ideal generated by x1 minus a1 to xn minus an. Right. So therefore, but we had that f a1 to an is equal to 0 since f x1 xn lies inside the kernel. So at the evaluation, it must yield 0. So uh, therefore, we will have the following that so if that is 0, that means uh, this evaluation, and we also have obviously that G A1 to AN should be equal to 0 since G lies in the kernel. I mean, G lies in this ideal. So when evaluated at A1 to AN, it should yield 0. So since F A1 AN is basically equal to summation of this BI1 to in of a1 power I1 till an power in plus g a1 an. We basically have that this is 0 and this is 0, which should imply that this term over here is also equal to 0. So that means that we have f x1 to xn is equal to g x1 to xn, and g belongs to x1 minus a1 to xn minus an, which implies that f belongs to this ideal xn minus an. Therefore, we achieve what we started out with. So f, we considered f to be any arbitrary element of the kernel, and we proved that it also belongs to this ideal generated by x1 minus a1. So we have that the kernel of theta A is a subset of this ideal MA. So we have proved the inclusion in both ways. So the kernel of theta A is equal to this ideal generated by x1 minus a1 till xn minus an. So this was the result. This was one of the results that we did want, since it was pretty much obvious by natural intuition and symmetry that this should be a maximal ideal. So now I will not prove the next result, although I will state it, and which is a special case of Hilbert's Nullstellan sets, is the exact converse. So it basically states that not only do we have that ideals of the form x1 minus a1 till xn minus an are maximal ideals, we also have that any maximal ideal is of the form x1 minus a1 till xn minus an, where a1 to an are uniquely determined. And this is basically version of the Hilbert's-Nullstellan sets for the n-variate complex polynomials. So I will not prove this since it uses a lot more advanced ideas of field extensions and field extensions being vector spaces over their basis fields. But it's just in general a nice theorem to keep in mind and to keep in hand. So now we can move on to the to some special cases of integral domains, and we'll try to see how we can generalize the notions of primes and divisibility in a more general setting here. So we start with the following. So, although it might have been discussed before, I'll just go over the definition once more. So, a ring R was known to be an integral domain or called an integral domain if there are no zero divisors inside the ring. That is, if a product AB is zero inside the ring, then either one of A should be equal to zero or B should be equal to zero. That is, we cannot have that the product of two non-zero elements is zero in the ring. So that's a fairly decent assumption to make because, well, uh, a lot of number theory that we actually do in any setting will rely on this fact that any two non-zero elements cannot have a zero product. So now we move on. So an element U of R is called a unit in R if U has a multiplicative inverse, U inverse in R. So this again is another uh, assumption. I mean, it's not an assumption. This definition of a unit is again important, and we'll see why. So we do know that in a ring, not every element has to have a multiplicative inverse, but we now consider the set of all elements that do have a multiplicative inverse in R, and we call them the units of R. What is important about these units is is these units are practically indistinguishable from one. So I'd like to state that practically indistinguishable in properties from one. And this is since U has a multiplicative inverse, we have that the ideal generated by U will be the ideal generated by one. And again, this is it should be fairly trivial since the ideal generated by U should contain U inverse, which should be equal to one, which implies one belongs to the ideal generated by U, which again implies that this ideal is contained in U. And the reverse inclusion is fairly trivial to prove again. So that is a unit in R. So in the ring Z, so let's say in Z, the units are 1, plus 1, and minus 1. Z contains two units. In fact, but obviously, as you could figure out, since a unit is basically an element of R that has a multiplicative inverse, a field is a ring where every element is a unit. I mean, where every non-zero element is a unit. So in R, every A belonging to R by R minus 0 is a unit. So and you'll see as we go on that units are basically indistinguishable from one in all their properties. The first such thing to that gave us evidence to this was the fact that an ideal generated by a unit is no different from the ideal generated by one, which is the ring itself. So now the second definition that we go to is that of divisibility. If A and B are two elements of R, then we have a notion of divisibility saying that A divides B if there exists some C in the ring R such that AC equal to B. So this basically means that A divides B if if AC equal to B for some C belonging to R. And this is basically, and if and only if, with the condition that the ideal generated by B is contained in the ideal generated by A. And again, that is fairly trivial since in the ideal generated by A, oh, wait, yeah, we have AC belongs to the ideal generated by A, which implies that B is, oh, again, my bad. Yeah, and AC is basically B, so B belongs to the ideal generated by A, and that should imply that ideal generated by B is contained in the ideal generated by A. Now, thirdly, we come to if A and B belong to an integral domain, and A is said to be a proper divisor of B if B is equal to AC for some C in R, that is uh, B divides A, but neither A nor C are units in R. So here, that will give the if and only if implication that B is a proper ideal contained in A, which is again a proper ideal contained in R. This proper inclusion is because we assume that A is not a unit. So if A is not a unit, the ideal generated by A cannot be all of R. So then we move on to another important definition the of A and B being associates. So in an integral domain, we have A and B are said to be associates if B is basically A into some unit. So again, we use we use a relative intuition that a unit is practically indistinguishable from one in its properties. So when you have that two elements are associates, which is an element is just a unit into some other element, then we have that B and A are also practically indistinguishable in many properties. And that is for that notion is further strengthened by the fact that if A and B are associates, then the ideals generated by both A and B are the same. Now, fifthly, we have already seen what it means to be irreducible in a polynomial ring. We generalize this notion of irreducibility in any integral domain R. So we say that an element A is irreducible in R if A equal to BC implies that either B or C is a unit in R. And in fact, A itself cannot be a unit since In the example of polynomial rings, we assume that for a certain polynomial f to be irreducible, it has to have degree greater than or equal to 1. So here we assume that a itself cannot be a unit, right? So a unit here is the same thing as an analog of degree 0 in a polynomial ring f of t. So this basically says that any non-unit A is an irreducible if it cannot admit any non-trivial decomposition where neither B or C is a unit. So, and this has a this has a both-way implication that A is a maximal ideal in R. And lastly, we come to the notion of a prime. And for an integral domain R, we say that an element A is a prime if A divides BC implies that A divides B or A divides C for all such BC in R. And of course, A cannot be a unit. And this is similar to the definition of primes that we use in our elementary number theory, which is P is a prime if P divides QR implies that either P divides Q or P divides R in the integers. And this has a two-way implication that BC lies in the ideal generated by A should either imply B lies in the ideal or C lies in the ideal. So now uh, we can use these definitions and move on and prove some interesting property. So first we start with something called a Euclidean domain, which should be fairly obvious as to what it implies. So an integral domain R is called a Euclidean domain if now, here we attempt to generalize the notion of the Euclidean division algorithm. So there we define a function sigma known as the size function for all non-zero elements of R. So sigma takes every non-zero element of R to a certain integer, a certain non-negative integer, and we denote this to be the size of that element. So now we have this notion of divisibility, or rather, the division algorithm for any A and B in R, there should be a unique Q and R in R. Actually, I forgot to mention this should be unique. There should be a unique Q and R in R such that A equals to BQ plus R, where either R is equal to 0 or the size of R is less than the size of the quotient. So this generalizes the unique divisibility algorithm in R, making it a Euclidean domain. So since in any arbitrary ring we don't have a natural order, so like the one that we do have in the integers, we need to use the size function when stating the express condition that the size of the remainder should be less than the size of the divisor. So some examples of Euclidean domains. So let's see. One such example will obviously be the integers themselves. So z, where the size function sigma from all non-zero integers to the non-negative integers is given by, well, sigma of A is equal to mod A. So this makes Z into a Euclidean domain. Secondly, where else have we seen the division algorithm? We've seen the algorithm in polynomials over a field. So if F is a field, Ft is also a Euclidean domain given by this is again very obvious from the standard way in which we do the division algorithm in polynomials over a field. So the size function takes all non-zero elements of the polynomial ring to the non-negative integers, and it is given by the size of the function, the size of the polynomial ft is equal to the degree. Since division is always done by degree in the inner field of in a ring of polynomials over a certain field. So the size of the polynomial is the degree itself. Well, a third non-trivial example that you may or may not have seen, but is an interesting one in its own right, is the field of something, or rather the ring of something known as the Gaussian integers. So the Gaussian integers, which is z of I, are basically the lattice in the space of complex numbers formed by the integers. That is the set a plus bi over complex numbers where a comma b belong to z. So these are the space of Gaussian integers. I mean, to visualize, if we took the complex plane, they'd form this nice square lattice spanning across the whole complex plane. So this is what the Gaussian integers would look like. So we can see that the Gaussian integers also form a Euclidean domain, also Euclidean domain. And here the size function, as one may expect, my bad, uh, the size function goes from the non-zero elements of the Gaussian integers to the non-negative elements of the integers, and the size function is given by z of a plus bi is equal to a square plus b square, which is basically nothing but the modulus of a plus bi. And I mean, I will not prove this, but it is very easy to verify that yes, these are in fact the this size function does in fact allow for a unique division algorithm. So now that we have in fact defined a Euclidean domain, we can go ahead and show that every Euclidean domain is in fact a principal ideal domain. So remember, I'll just define, I mean, I won't define a PID, I'll just give a short definition. Every ideal is principal, is generated, and that means every ideal is generated by a single element. So let's go about showing this. So let's just take any ideal of a Euclidean domain. So we just have to show that R is a Euclidean domain implies that R is a PID. So let R be a Euclidean domain. So, and let I be an ideal of R. Okay. So we have these two standing assumptions. So choose some uh, A in I. Of course, A is not equal to zero. Like choose some non-zero A in I. And of course, if we cannot have any non-zero A in I, then I is, of course, the zero ideal, and which is generated by a single element. So we don't have to worry about that case. Such that choose some non-zero A in I such that sigma A is minimum. And we can do this since sigma A lies in the positive non-negative integers, and we have the well-ordering principle. So there is always a least element over there. So therefore, we have that sigma A is minimum and A belongs to I. So therefore, the ideal generated by A is also contained in I. Now, if B belongs to I, since since R is a Euclidean domain, we have that due to the division algorithm, there exists Q and R belonging to R, so that B equal to AQ plus R, right? Where R is equal to zero or sigma of R is less than sigma of Q. But now here will come our contradiction. So our contradiction will come from here. If If R is not equal to zero, that will imply that sigma R is less than sigma Q. But now we have B is equal to AQ plus R. And we assume that B belongs to I. This belongs to I. And since A belongs to I, that means this whole thing AQ will also belong to I. So we have B minus AQ will also belong to I, which implies that R belongs to I. But if R belongs to I, sigma R cannot be less than sigma of, oh, my bad. This is not sigma of Q. That is not what the division algorithm states. It is sigma of the divisor, or the size of the divisor, which is sigma of A. My bad. Yeah, sigma of A. So, and that will imply that sigma of R is less than sigma of A, which is contradicts the minimality of sigma A. Contradict the minimality of sigma of A. So this is basically a contradiction. Therefore, we must have that R is equal to 0. Therefore, for any B belonging to I, we have A divides B. So that implies the I is fully contained in the ideal generated by A. So we have both inclusions, therefore I is equal to the ideal generated by A, which implies I is principal. Therefore R is also a PID, since any ideal I is a principal ideal in R. So now uh, we define the notion of the greatest common divisor, just like we did for the rings before. So we say let R be an integral domain. Let let A and B be any two elements in R that are non-zero. So then we define the greatest common divisor of A and B to be similar to elementary number theory over the integers. We have that it is an element D such that D should divide both A and B in R. And if E belongs to R, then and if E divides A and E divides B, then E should divide D in R. So this is the exact same two definitions that we use for the integers. It has just been generalized over to any arbitrary integral domain. So now here we have a further caveat to face. The problem is in an arbitrary integral domain, we can have that there may be more than one GCD of two elements. So and we don't have to worry much about that because it is easy to show that if E and D are two GCDs of A and B in R, then the ideal generated by E is the same as the ideal generated by D, which will imply that E and D are actually associates in R, which is that is E is equal to D into some unit in R. So so they are not too different. In fact, one is just a unit into another into the other one. So this allows them to share many of the similar properties that we might want to expect for if we have more than one greatest common divisor in R. So now, if R is a principal ideal domain, then for any two ideals, A and B of R, we will have that the ideal generated by A and B is also principal ideal, which could be which for which there'll exist some element D such that it is generated by D, and this D in fact serves as the greatest common divisor of A and B in any principal ideal domain. So hence, we can even conclude that in a PID, any two non-zero elements have a GCD, right? So this is a very nice result. In fact, there is a much greater generalization of such integral domains in which any two elements contain a GCD, and they are very aptly called GCD domains, but we will not be getting into them. So I seem to have accidentally stated this again. So yeah, we have the following. I don't know why I had to write this again. So yeah, in any PID, any two non-zero elements have a greatest common divisor. So now we move on to the last kind of integral domain that we will consider in this talk, and that is something known as a unique factorization domain. So now that we have seen the notions of primes and divisibility, we'd actually like to go further and ask, okay, now that we do know what primes are, what are the integral domains where we can expect to see things like a unique prime factorization? And those are precisely the unique factorization domain. So an integral domain R is called a unique factorization domain, or more shortly a UFD, if for any element A in R and any non-zero element A in R, there are primes P1 to PR in R and a unit U in R such that A can be expressed as P1 into PR till PR into U. So, and we say that this decomposition is unique up to the sense that if if Q1 QR if Q1 to QR dash into U dash and P1 to PR into U are two such prime decompositions of A, then there are the exact same number of primes in both the decompositions, which is R is equal to R dash. And we also have that every QI is basically the associate of some PI, meaning every QI is basically some unit into a PI. So QI and PJ are associates, meaning for every QI in this part of the decomposition, we can find a PJ such that QI and PJ are associates. And basically, we can start pairing the primes one by one. And since being associate makes them more or less the same, since they only differ by a factor of a unit, which is a very trivial element in R, we have that this decomposition is the same. So this decomposition is unique up to this sense. So uh, I mean that is a pretty fair assumption to make, since we can have two different primes that divide the same element, and the primes themselves are associates. Since being an associate of the other does not really change the properties in a very large way. So now we already showed that Euclidean domains are in fact principal ideal domains. So if this was the space of Euclidean domains, then we have that it is contained in the space of principal ideal domains. Now we have that if R is an integral domain, then all its prime elements are irreducible. And remember, there is a difference between the definition of prime and the definition of an irreducible, which I will go back to. The first, irreducible, was that if A is equal to BC, then either B or C is a unit, meaning A cannot be further reduced to two non-trivial elements of R. That was the definition of irreducible, which was different from the definition of a prime. A prime is if an element A was a prime if A dividing BC implied that A divided B or A divided C. So these were in fact two different definitions, and hence we could not consider irreducibles to be prime, although irreducibles are primes in most of the domains that we deal with in elementary number theory, which is the integers. But we will show that in an integral domain, every prime element is irreducible. So basically, our theorem states that in an integral domain, every prime is irreducible. Yeah. So this is what we want to prove over here. And this is a very trivial proof. So let A be a prime in the integral domain R. So let A equal to some BC. We just, so since A is a prime, we have A divides B or A divides C. We need to show that it is, and we need to show that A is irreducible. So we need to show basically that either B or C is a unit. Either B or C is a unit, right? So now, since we have A divides B or A divides C, we can, without loss of generality, we can assume let let A divide B. So that implies B equal to AX for some X belonging to R. So that implies A, which is equal to BC, is equal to AXC, which implies A into 1 minus XC equal to 0. But R is an integral domain. So when we have a product A into something to which is equal to 0, we should either have that A is equal to 0 or 1 minus XC is equal to 0. But we cannot have A is equal to 0 since A is a prime. So 1 minus XC is equal to 0. So that implies 1 minus XC is equal to 0. which implies xc equal to 1. Therefore, x is the multiplicative inverse of c, uh, or I'd rather say this in a more short manner. I would say x is equal to c inverse, which implies that c is a unit. Therefore, a equal to bc implies that either b or c is a unit. We assume that a divides b, and we show that therefore c is a unit. Or if we didn't assume that and instead assume that a divides c, then we could similarly show that b is a unit. So therefore, a is irreducible. Uh, Therefore, A is irreducible. So we see that every prime in an integral domain is in fact also an irreducible. Now if we and this theorem held true for all integral domains, right? So well, let's let's try to visualize this. If this was the space of all integral domains, then we had the fact that all primes are irreducible, right? But now, if we go into the space of integral domains and we just consider the space of all PIDs, right? Then we have that, in fact, inside here, not only are all primes irreducibles, we have that all irreducibles are also prime. So we would basically want to prove this statement of the theorem. So that would imply that in a PID, we have that the set of primes are precisely the set of irreducibles. So we want to prove the theorem. If R is a PID, then all irreducibles of R are primes, which is again another trivial theorem. So uh, we start. So we basically have to show that if A is an irreducible in a PID, then A is a prime. So we start with our standing assumption. Let A in the integral domain. Oh, my bad. Yeah. Let A belong to the integral domain and let A be irreducible. So A divide some let A divide some BC. If A does not divide B, then let D be the greatest common divisor of A and B. Therefore, D divides A and D divides B. So, therefore, we have du equal to A for some u belong to R. And since our standing assumption that A is irreducible, either D or U is a unit in R. I mean, we have A equal to du and A is irreducible. Therefore, either D or U is a unit in R. So what does that imply? If U is a unit, then D is an associate of A, since D is basically, or I mean, since A is basically D into the unit U, so it's an associate of A. Therefore, D is basically A U inverse, since A is DU. So, and we have that D dividing B will imply that B equal to dV for some V belonging to R. So that implies B equal to U inverse V, and that will imply A divides B. But that is a contradiction. So therefore, we must actually have D. Therefore, D should be a unit and not U, which would imply the ideal generated by 1 is equal to ideal generated by D, which is ideal generated by AB. And that will imply 1 belongs to the ideal generated by AB. That means 1 is of the form RA plus SB for some R comma S belong to R. Again, if you can see, this is similar to Bezout's lemma. And again, there is a whole set of domains for in which Bezout lemma holds, and they are precisely known as Bezout domains. But again, we won't get into that. That implies C equal to RAC plus SBC, which imply, and therefore A dividing BC implies that A divides RAC plus SBC, which implies A divides C. Therefore, A is prime. So in a PID, all irreducibles are also primes. Therefore, in a PID, the set of all irreducible are precisely the set of all primes. We have that. Now, finally, we have the following theorem that principal ideal domains are in fact unique factorization domains. So again, to visually give where we are going, we had that Euclidean domains are lie completely inside the space of principal ideal domains, and we show that every principal ideal domain is also a unique factorization domain. That is, the unique factorization theorem holds in the principal ideal domains, and that is another simple theorem which we will prove and end this talk with, which is, so we start with the starting assumption that R is a PID. So let A belong to R. So that A is non-zero and A is not a unit. So A is a non-zero non-unit element of R. So if A is irreducible, then A is a prime. And trivially, it has a unique factorization. It has a unique prime decomposition. So trivially, A will then have a unique prime decomposition. But this was only assuming that A is irreducible. So now, if A is reducible, on the contrary, if A is reducible, then A is equal to some BC, where we can say that B and C are not units in A. So we have this, then we can then continue this. I mean, if at every stage, each of these individual non-unit factors is also irreducible, then, I mean, is also reducible, then then we can continue this infinitely, getting a kind of tree. So there exists a sequence A equal to A naught, followed by A1, A2, and so on, which all lies in R, meaning this whole sequence is contained in R. So where AI is a proper divisor of AI minus 1 for all I. If that is, if at every stage we get that every factor is reducible. But now we can show that this is a contradiction. So if this sequence goes and where AI is a proper divisor of AI minus 1, that means we will also have an inclusion of ideals. And that too, this will be a proper inclusion since we are talking about proper divisors here. So A2, so on. But and each of these is an idea. So we will have I naught is right. Yeah, I naught is contained in I1, which is contained in I2, so on. But again, this is a chain, and this chain is bounded by the ideal I given by taking the union of all such ideal. It's bounded by this. And since R is a PID, that will imply I is principal, which implies that I is actually equal to some A dash for it's generated by a single element A dash for some A dash belong to R. So that implies that Uh, so that implies B belongs to AK for some index K, which will imply that B belongs to AI for all I greater than or equal to K. So actually, wait, sorry, my bad. So since it is bounded, we have that A dash belongs to AK for some index K, right? It is bounded by this ideal, and therefore A dash belongs to AI for all I greater than or equal to K. That implies that AI is the same as A dash for all I greater than or equal to k. That means this sequence actually not terminates but becomes constant since we reach a dash at some point in this sequence of ideals. That is, a naught is included in a1 is included in till some ak, but after ak, all the ideals are equal to the ideal generated by a dash. So this is equal to ak plus 1, which is equal to ak plus 2, and this equality continues. So that means this proper inclusion actually only holds to a certain point, and then after this, all the ideals are equal. So therefore,
Are
this
we using some form of Zorn's lemma here?
yes, we are using Zorn's lemma over here, since we are using the fact that it will be bounded above. We used the fact that this ideal that we defined over here actually bounds this entire sequence of ideals over here. So it's not exactly Zorn's lemma, but we are using a setup of the fact that this chain is bounded using the methods that we use to prove Zorn's lemma. So this sequence terminates, in fact, and it cannot go on endlessly. So therefore, every irreducible. So you cannot continuously keep getting more and more irreducible divisors of A. So ultimately, you have to terminate in every chain that you go below. So therefore, every irreducible decomposition will end up being finite. So therefore, every prime decomposition, prime decomposition will be finite. Therefore, every non-zero non-unit A in this PID will admit, uh, sorry, yeah. So every non-zero non-unit A that belongs to this integral domain will actually admit a finite prime decomposition. So we have that a prime decomposition exists for all such things belonging to the unique factorization domain. And it is a very trivial proof that this unique factorization decomposition, I mean, this prime decomposition is unique up to the sense that we defined before. So I will not be proving that, although I will just leave that as a trivial lemma. This factorization is in fact unique up to associates. And this basically concludes the final talk in this final talk of mine in this series about integral domains. So, were there any other questions? Okay, I guess not. In that case, uh, I think the next few talks will be taken by other people and they will go on more into the introduction of modules, etc. So I guess that's it for this talk then.
Now we'll move on to questions. If anybody has questions, please ask.